The notion first occurred to me during a particularly striking sunset over the Pacific. As the sun's dying rays stretched across the horizon, setting the clouds ablaze with hues of crimson and gold, I found myself contemplating the boundaries of our universe, and whether they might be more constrained than we typically imagine. What if our entire observable universe exists within a black hole? The idea sounds like science fiction, but as we delve deeper into the mathematics of cosmology and the physics of these cosmic leviathans, surprising parallels emerge that have led serious physicists to consider this possibility. When we think of black holes, we typically envision cosmic vacuum cleaners, regions of space where gravity is so intense that nothing, not even light, can escape. Their boundaries, called event horizons, represent points of no return. Cross this threshold, and you are forever cut off from the outside universe. But what might exist within that boundary? And could our universe, with its billions of galaxies stretching across billions of light years, actually be the interior of one of these cosmic giants? The seeds of this idea were planted in 1965 when mathematician Roy Kerr solved Einstein's field equations for rotating black holes. Unlike the simpler Schwarzschild black holes, which are perfectly spherical and non-rotating, Kerr black holes spin, creating distortions in spacetime that potentially allow for exotic phenomena, including, theoretically, passages to other universes. To understand why the universe as a black hole theory has scientific merit, we must first examine the surprising similarities between black hole interiors and the broader cosmos. Both are expanding regions governed by general relativity, both contain matter and energy, and both have boundaries beyond which information cannot travel. The mathematics describing the interior of certain black holes bears striking resemblances to the equations describing expanding universes. In 1981, physicist Alan Guth proposed the inflationary theory of cosmology, suggesting that our universe underwent a period of exponential expansion in its earliest moments. This rapid inflation shares mathematical properties with certain solutions describing black hole interiors. Robert Mann, a physicist at the University of Waterloo, explained it this way: the interior of a black hole can be mathematically mapped to an expanding universe model. This is not merely an interesting coincidence, but a profound connection that emerges from Einstein's equations. The comparison becomes even more compelling when we consider the total mass-energy content of our observable universe. If we were to compress all the mass energy in our observable universe to a radius smaller than its Schwarzschild radius, approximately 10 billion light-years, it would indeed form a black hole. Remarkably, this calculated Schwarzschild radius is roughly comparable to the current size of our observable universe. This coincidence did not escape Nikodem Poplawski of the University of New Haven. In 2010, he published a paper suggesting that our universe might be the interior of a black hole that exists in another, larger universe. His model addressed several cosmological puzzles, including the horizon problem, the question of why distant regions of the universe appear to have the same temperature despite never having been in causal contact. But how could a universe form inside a black hole? The answer might lie in what happens when matter crosses the event horizon of a rapidly rotating black hole. In traditional models, matter falling into a black hole would be crushed at the singularity, a point of infinite density at the center. However, in more complex models involving rotating black holes, singularities might be avoided. Poplawski's work built on ideas from Russian physicists Vitaly Ginzburg and Lev Landau, who in the 1950s developed theories about the behavior of matter under extreme conditions. Poplawski proposed that when matter falls into a black hole, the increase in torsion, a property of spacetime related to rotation, could cause a bounce rather than a crush at the center, creating a new, expanding region of spacetime, potentially a new universe. This concept aligns with Einstein's general theory of relativity, which describes gravity not as a force but as a curvature of spacetime caused by mass and energy. The intense curvature inside a black hole could, theoretically, curve spacetime so extremely that it creates what topologists call a non-trivial manifold, essentially a new region of spacetime with its own physical laws and evolution. The idea gained further traction in 2006 when string theorists exploring black hole thermodynamics discovered unexpected connections between black hole event horizons and cosmic horizons. These theoretical explorations, led by string theorist Leonard Susskind at Stanford University, suggested that information falling into a black hole might be encoded on its horizon, similar to how information about our universe might be encoded on a cosmic horizon. But if our universe is within a black hole, would not we be crushed by gravity? The answer lies in the difference between experiencing a black hole from the outside versus from the inside. From the outside, a black hole appears as a region from which nothing can escape. But from the inside, the mathematics suggests a different experience, one that could match our observations of an expanding universe. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that permeates our universe. Discovered in 1965 by Arno Penzias and Robert Wilson, this radiation is remarkably uniform in all directions, with tiny fluctuations that map to the earliest structures in our universe. The pattern of this radiation matches what we might expect if our universe expanded from a singularity-like condition, precisely the kind of condition that might exist inside a black hole. The theory also provides an elegant explanation for the arrow of time, why time appears to flow in one direction despite the time symmetry of most physical laws. Inside a black hole, the inward direction of spacetime creates a natural time asymmetry, potentially explaining our perceived arrow of time from past to future. But if our universe is inside a black hole, can we ever know what lies outside? Here we encounter a profound limitation. Just as information cannot escape a black hole's event horizon, information from the parent universe cannot enter our universe from beyond our cosmic horizon. We are, in a very real sense, causally disconnected from whatever exists outside. This disconnect highlights one of the theory's strengths. It is largely consistent with our observations while making few testable predictions that would distinguish it from conventional cosmology. This presents both a philosophical challenge and a scientific opportunity. How do we test a theory about what exists beyond our observable limits? One potential avenue involves quantum entanglement. In 2016, physicists Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully proposed the firewall paradox, which suggests that quantum entanglement might behave unusually near black hole horizons. If our universe's boundary is indeed a black hole horizon, subtle quantum effects might be detectable at the edges of our observable universe. Another approach examines the cosmic microwave background for patterns that might indicate we are inside a black hole. Certain geometrical features, if detected, would support the theory. In 2020, astrophysicists analyzed data from the Planck satellite, looking for these signatures. While they did not find definitive evidence, they did not rule out the possibility either. The black hole universe theory also offers insights into dark energy, the mysterious force accelerating our universe's expansion. Discovered in 1998 by two independent teams led by Saul Perlmutter and Brian Schmidt, dark energy has puzzled physicists for decades. In the black hole model, this acceleration emerges naturally from the geometry of spacetime inside a black hole, potentially eliminating the need for an exotic form of energy. But what about black holes within our own universe? If our universe is inside a black hole, and our universe contains black holes, could each of those black holes contain other universes? This nested or fractal structure of universes within black holes within universes creates a compelling vision of cosmic reproduction. Lee Smolin of the Perimeter Institute proposed exactly this in his theory of cosmological natural selection, first articulated in 1992. Smolin suggested that black holes might be the means by which universes reproduce, with each black hole giving birth to a new universe with slightly different physical constants. Over time, this process would favor universes that produce many black holes, just as natural selection favors organisms that reproduce successfully. The mathematics supporting these ideas draws from several branches of physics. Quantum field theory in curved spacetime, developed by Stephen Hawking and others in the 1970s, provides tools for understanding how quantum fields behave in strongly curved regions like those near black hole horizons. Loop quantum gravity, a theory developed by Carlo Rovelli and others since the 1990s, offers mathematical frameworks for understanding spacetime at the quantum level, potentially avoiding the singularities that plague classical black hole models. If we examine the implications further, the theory suggests our universe might have been born from matter collapsing into a black hole in another universe. The extreme conditions of this collapse, similar to but distinct from our concept of the Big Bang, would have set the initial conditions for our universe's evolution. The timing of cosmic inflation, occurring a fraction of a second after the universe's birth, aligns with theoretical models of what happens when matter crosses a black hole's inner horizon. This inner horizon, distinct from the outer event horizon, is where infalling matter would experience extreme conditions that could trigger something like inflation. What would it mean for humanity if this theory were proven correct? Beyond the scientific implications, it would fundamentally alter our cosmic perspective. We would not exist in an independent universe but rather in one bubble in a potentially infinite cosmic foam of universes, each contained within black holes in their parent universes. This nested structure would not diminish our existence but rather place it within a grander cosmic context, one where universes themselves may evolve and reproduce. Our physical laws, from the strength of gravity to the mass of elementary particles, might not be arbitrary but rather the result of a long chain of cosmic evolution optimized for black hole production. The mathematics of this theory involves sophisticated concepts from general relativity and quantum theory. The Einstein field equations, which describe how spacetime curves in response to matter and energy, allow for solutions where spacetime extends beyond black hole horizons into new regions. In the language of differential geometry, these extensions are called maximal analytic extensions, and were first explored by mathematicians like Roger Penrose in the 1960s. In rotating black holes described by the Kerr metric, these extensions become particularly interesting. The spacetime inside contains regions where the radial dimension behaves like time, and time behaves like space, a perfect mathematical description of a universe where space expands with time. The boundary between these regions, called the Cauchy horizon, could correspond to the beginning of our universe. Recent work in quantum gravity has strengthened these connections. In 2014, physicists led by Ted Jacobson at the University of Maryland found that when quantum effects are included, the interior of certain black holes can avoid forming a singularity, instead bouncing into an expanding region that looks remarkably like an inflating universe. These models address one of the major obstacles to the black hole universe theory, the problem of singularities. Classical general relativity predicts that the center of a black hole contains a singularity where physics breaks down. However, most physicists believe a complete theory of quantum gravity will eliminate these singularities, replacing them with more physically realistic structures. String theory, one candidate for quantum gravity, suggests that singularities might be replaced by complex arrangements of fundamental strings. In 2009, theoretical physicists calculated that under certain conditions, these string configurations could lead to the birth of new inflating regions of spacetime, essentially new universes. But what about the observational evidence? Can we actually test whether we live inside a black hole? While direct verification remains challenging due to cosmic horizons, several indirect tests have been proposed. One approach examines the cosmic microwave background radiation for signs of unusual geometry. If our universe formed inside a black hole, its earliest moments might have imprinted subtle patterns on this radiation. In particular, a lack of correlations between opposite sides of the sky, what physicists call quantum entanglement across the sky, could indicate we are inside a black hole. Another test involves looking for unusual patterns in the distribution of galaxies on the largest scales. In 2019, astronomers using data from the Sloan Digital Sky Survey found intriguing large-scale structures that might be consistent with the geometry of a black hole interior, though alternative explanations exist. The theory also makes predictions about primordial gravitational waves, ripples in spacetime from the universe's earliest moments. These waves, if detected with specific properties by experiments like LIGO or future space-based detectors, could provide evidence for or against the black hole universe model. The black hole universe theory connects to other frontier areas of physics as well. The holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, suggests that all information in a volume of space can be encoded on its boundary. If our universe is inside a black hole, our cosmic horizon might function as such a boundary, encoding all the information within our universe. This holographic relationship has deep implications for quantum gravity and information theory. It suggests that, in a sense, our three-dimensional reality might be a projection of information encoded on a two-dimensional surface, the cosmic horizon or black hole boundary that encloses our universe. The theory also intersects with multiverse concepts, which have gained traction in theoretical physics. Rather than envisioning parallel universes as physically separate, the black hole universe model connects them through higher dimensional spacetime, with each universe existing inside a black hole of another universe. Theoretical physicist Jude McFadden of Imperial College London captured this idea eloquently. Black holes might be the umbilical cords that connect universes in a vast cosmic network, each genesis coming from the collapse of matter in another cosmos. This perspective transforms our understanding of cosmic evolution. Rather than our universe having a singular beginning and eventual end, it might be part of an eternal process of universe creation and evolution. Each black hole formed in our universe might give birth to a new universe, with slightly different physical parameters. Over cosmic timescales, this process would favor universes that produce many black holes, possibly explaining why our universe seems so conducive to forming complex structures, including stars, galaxies, and black holes. The physical constants that govern our universe, from the strength of forces to the masses of particles, might not be random but rather optimized through a form of cosmic natural selection. This evolutionary perspective resonates with developments in other fields of science. Just as biological evolution explains the complexity and diversity of life without requiring a designer, cosmic evolution might explain the apparent fine-tuning of our universe's physical parameters without requiring a cosmic designer. The theory has gained increased attention with recent discoveries about black hole information. Stephen Hawking's work in the 1970s suggested that black holes slowly evaporate through a process now called Hawking radiation, potentially destroying information about what fell in, a problem known as the black hole information paradox. Recent theoretical work, particularly by Juan Meldacena and Leonard Susskind, suggests that quantum entanglement might allow information to escape black holes through wormhole-like connections. If correct, this could mean that information about our parent universe might be subtly encoded in the cosmic microwave background radiation or other cosmological features. The mathematics describing these connections draws from advanced concepts in quantum information theory, tensor networks, and holography. In 2013, physicists demonstrated that certain quantum systems can be described mathematically as geometric spaces with properties similar to those of black hole interiors, suggesting deep connections between quantum information, black holes, and potentially the structure of our universe. If our universe is indeed inside a black hole, it raises questions about the nature of the Big Bang. Rather than representing the absolute beginning of everything, the Big Bang might better be understood as a transition, the point where matter collapsing in another universe crossed a boundary and began expanding in ours. This reframing helps address one of cosmology's persistent puzzles: why the Big Bang appears to have been highly ordered rather than chaotic. The entropy, a measure of disorder, of the early universe was remarkably low, which has been difficult to explain in conventional cosmology. If our universe formed from matter collapsing into a black hole, this initial order might have arisen from the physics of the collapse process. The theory also offers new perspectives on the ultimate fate of our universe. Conventional models suggest several possibilities: a continued acceleration leading to a big freeze, a reversal of expansion leading to a big crunch, or various other scenarios. The black hole universe model suggests our universe might continue expanding indefinitely within its parent black hole, eventually becoming dark and diffuse but never truly ending. What about the physics of the parent universe? While we cannot directly observe it, the mathematics of general relativity allows us to make some inferences. The parent universe would need to have similar physical laws to our own, at least similar enough to allow for black hole formation. However, constants and parameters might differ, potentially dramatically. The black hole universe theory also intersects with theories of quantum gravity, particularly loop quantum cosmology developed by Abhay Ushtekar and others since the 1990s. This approach suggests that the extreme conditions at the beginning of our universe or inside a black hole would trigger quantum gravitational effects that cause a bounce rather than a singularity. Exactly what we would expect if our universe formed inside a black hole. Recent computer simulations support this possibility. In 2020, physicists used supercomputers to model the collapse of matter into rotating black holes, finding that under certain conditions, the collapsing matter could avoid forming a singularity and instead bounce into an expanding region, mathematically similar to an inflating universe. These simulations build on earlier work by physicists like Nikodem Poplawski, who in 2012 calculated that the torsion, a property related to the spinning of spacetime, in a collapsing black hole could cause matter to bounce rather than crush, creating a new expanding universe. What would an observer falling into a black hole experience? According to calculations based on general relativity, they would cross the event horizon without noticing anything special at that boundary. However, as they continued deeper, they would eventually reach a point where space and time exchange roles. What had been the inward direction would become a temporal direction. They would be moving forward in time while experiencing an expanding space around them, much like our experience in our expanding universe. This perspective shift helps explain why we do not feel like we are inside a black hole. Our cosmic experience, galaxies moving away from us in an expanding universe, is precisely what the mathematics predicts for the interior of certain black holes. The theory also provides an interesting perspective on cosmic inflation, the period of exponential expansion in our universe's earliest moments. Proposed by Alan Guth in 1981, inflation solves several cosmological problems but has always needed a mechanism to explain what caused it. If our universe formed inside a black hole, inflation could be a natural consequence of matter crossing certain horizons within the black hole. In 2017, physicists led by Raul Carballo Rubio at the International School for Advanced Studies developed models showing how quantum effects near black hole horizons could trigger inflation-like expansion, providing a potential mechanism for universe formation within black holes. This approach also addresses one of the persistent questions about inflation. Why did it start and then stop? In black hole universe models, the transition of matter across specific boundaries within the black hole naturally creates a brief period of exponential expansion followed by slower expansion, matching what we observe in our cosmic history. The geometry of black hole interiors also helps explain cosmic homogeneity, why the universe looks roughly the same in all directions on large scales. As matter falls into a black hole, it experiences extreme stretching and compression that would tend to smooth out irregularities, potentially explaining why our early universe was so remarkably uniform. What about the cosmic constants that govern our universe? From the strength of gravity to the mass of the electron, these values seem finely tuned for complexity and life. In the black hole universe theory, these constants might not be arbitrary but rather the result of cosmic evolution favoring universes that produce many black holes. Physicist Lee Smolin has calculated that universes that produce many black holes tend to have physical constants similar to our own. If universes reproduce through black holes, then over many generations, universes with constants favorable to black hole production would become more common, potentially explaining why our universe has the properties it does. This evolutionary approach provides an alternative to the anthropic principle, which suggests we observe our universe's properties because they allow for observers like us. Instead, our universe might have its properties primarily because they are good for producing black holes, with the ability to support life being a secondary consequence. The black hole universe theory has implications for fundamental questions about time. If our universe formed from matter collapsing in another universe, does that mean our parent universe existed before ours? The answer is both yes and no. From the perspective of an observer in the parent universe, the black hole that contains our universe exists within their timeline. But time inside our universe is disconnected from time in the parent universe. Our beginning is not directly connected to any particular moment in the parent universe's time. This disconnection relates to how general relativity treats time. Rather than being absolute, time is part of the space-time fabric, which can bend, stretch, and even disconnect between different regions. Our universe's time dimension is not a continuation of the parent universe's time, but rather a new dimension emerging from the geometry of the black hole interior. Recent developments in quantum gravity strengthen these connections. In 2019, physicists developed models showing how quantum effects could transform a black hole singularity into a bridge to a new expanding universe, providing a potential mechanism for universe creation without requiring a true beginning of time. These models build on earlier work in string theory, particularly the concept of fuzzball black holes developed by Samir Mather and others since the early 2000s. In this approach, black hole interiors are not empty space with singularities but rather complex configurations of fundamental strings. These configurations could potentially spawn new expanding regions with their own effective laws of physics, essentially new universes. What would happen if we could somehow visit the boundary of our universe, the cosmic horizon that might correspond to the black hole event horizon? The mathematics suggests we could never reach it, just as an observer inside a black hole cannot return to the event horizon after crossing it. Our cosmic horizon continuously recedes as we approach it, always remaining beyond reach. This unreachable boundary creates what physicists call a cosmic censorship, a fundamental limit to what we can observe and test. However, this limitation does not make the theory unscientific. Many cosmological theories involve regions beyond our observable universe, and their scientific value comes from their explanatory power and consistency with what we can observe. The black hole universe theory also connects to quantum field theory through the concept of vacuum energy. In quantum field theory, empty space is not truly empty but filled with quantum fluctuations, virtual particles briefly popping in and out of existence. These fluctuations contribute energy to space itself, creating what we call vacuum energy or dark energy. In 2023, physicists developed models showing how the vacuum energy in a universe inside a black hole would naturally have the properties we observe in our universe. Specifically, a small positive value that causes accelerated expansion. This provides a potential explanation for one of cosmology's biggest puzzles: why dark energy has the precise value it does. These connections to quantum field theory extend to the early universe as well. The extreme conditions during the universe's formation, whether in a conventional Big Bang or during matter crossing certain horizons in a black hole, would amplify quantum fluctuations, creating the seeds for later structure formation. The pattern of these fluctuations, visible in the cosmic microwave background radiation, matches what we would expect if our universe formed in conditions like those inside a black hole. The black hole universe theory also offers perspectives on cosmic topology, the overall shape of our universe. While locally our space appears flat, parallel lines remain parallel, the global topology could be more complex. If our universe formed inside a black hole, its global topology might resemble a higher dimensional analog of a sphere, finite yet unbounded. This topology would have observable consequences. In a universe with spherical topology, light could potentially travel all the way around the universe, leading to repeated or periodic structures in the night sky. Astronomers have searched for such patterns without definitive results, though the immense size of our observable universe makes detecting such patterns challenging. Recent observations of the cosmic microwave background have revealed several anomalies, unexpected features that do not fit perfectly with standard cosmological models. These include the cold spot, an unusually cool region, alignment of certain large-scale patterns, the so-called axis of evil, and lower than expected correlations between distant points. While not conclusive, some theoretical physicists have suggested these anomalies might be consistent with our universe having formed inside a black hole. The theory also connects to the study of primordial black holes that formed in the earliest moments of our universe. If our universe formed inside a black hole, the extreme conditions during this formation might have created numerous smaller black holes within our universe. Recent observations have found evidence for unexpected populations of black holes, potentially supporting this prediction. What about dark matter, the mysterious substance that appears to hold galaxies together despite being invisible? In certain versions of the black hole universe theory, dark matter emerges as a natural consequence of how matter from the parent universe crosses into our universe through the black hole. The mathematics suggests this process would create a form of matter that interacts gravitationally but not through other forces, exactly matching the properties of dark matter. This approach to dark matter differs from conventional explanations, which typically involve new particles not in the standard model of particle physics. Instead, it suggests dark matter might be a geometric effect related to how our universe formed inside a black hole. The black hole universe theory also provides insights into cosmic acceleration, the discovery that our universe's expansion is speeding up rather than slowing down. This discovery, which earned the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees, has been difficult to explain in conventional cosmology without invoking dark energy. In the black hole universe model, this acceleration emerges naturally from the geometry of spacetime inside a black hole. As matter crosses certain boundaries within the black hole, it experiences an effective gravitational repulsion rather than attraction, creating an accelerating expansion similar to what we observe. This geometric explanation for cosmic acceleration connects to ideas first explored by Einstein himself. In his original formulation of general relativity, Einstein introduced the cosmological constant, a term representing energy inherent to space itself, to create a static universe. He later called this his greatest blunder when observations showed the universe was expanding. Ironically, modern observations indicate the cosmological constant may be real after all, driving cosmic acceleration. In the black hole universe model, this cosmological constant is not an arbitrary addition but a natural consequence of the geometry of spacetime inside a black hole. The mathematics of general relativity shows that certain regions inside black holes have properties equivalent to a positive cosmological constant, exactly what we observe in our accelerating universe. Recent theoretical work strengthens these connections. In 2022, physicists developed models showing how quantum effects near black hole horizons could create regions with effective cosmological constants matching the value we observe in our universe. These calculations use techniques from both string theory and loop quantum gravity, suggesting the connection is robust across different approaches to quantum gravity. What about the multiverse implications? If each black hole gives birth to a new universe, and our universe contains billions of black holes, does that mean billions of new universes are constantly being created? The mathematics suggests yes, we might be part of a vast and continuously growing multiverse, with each black hole in our universe potentially containing another universe with its own galaxies, stars, planets, and possibly life. This perspective transforms our understanding of cosmic evolution and diversity. Rather than our universe being unique or special, it might be one among countless others, each with potentially different physical laws and constants. This vast diversity would emerge naturally from the physics of black holes, without requiring any external design or fine-tuning. The theory also connects to information theory through the concept of entropy. In thermodynamics, entropy measures the disorder or randomness of a system. Black holes have enormous entropy, proportional to their surface area rather than their volume, as calculated by Jacob Bekenstein and Stephen Hawking in the 1970s. If our universe exists inside a black hole, its total entropy would be bounded by the surface area of its cosmic horizon, matching mathematical limits derived from holographic principles. Recent calculations show that our observable universe has an entropy remarkably close to what would be expected if it were inside a black hole. This entropy connection extends to the beginning of our universe. One persistent puzzle in cosmology has been why the early universe had very low entropy despite emerging from the extreme conditions of the Big Bang. The black hole universe theory suggests an explanation. The process of matter crossing certain horizons within a black hole naturally creates regions of locally reduced entropy, potentially explaining the thermodynamic arrow of time in our universe. The theory also provides perspectives on quantum gravity, the elusive theory unifying quantum mechanics and general relativity. Inside a black hole, space-time curvature becomes extreme, requiring a quantum treatment of gravity. If our universe formed inside a black hole, its earliest moments would have been governed by quantum gravitational effects. Recent approaches to quantum gravity, including causal set theory developed by Raphael Sorkin and others since the 1980s, provide mathematical frameworks that naturally accommodate the idea of universes forming inside black holes. These approaches suggest that space-time at the quantum level consists of discrete elements connected by causal relationships, a structure that allows for the birth of new space-time regions through processes similar to black hole formation. The implications extend beyond physics to philosophy and our place in the cosmos. If our universe is one among many, with each black hole containing another universe, it fundamentally changes our cosmic perspective. Rather than being central or special, our universe becomes one link in an infinite chain of cosmic reproduction and evolution. This perspective does not diminish human significance but rather places it within a grander context, one where complexity and life might be features emerging across countless universes, each with its own history and future. The physics that allows for our existence might not be unique to our universe but rather common among universes that evolve to produce many black holes. As we ponder these profound connections between black holes and universes, we might wonder, could we ever communicate with or travel to these other universes? The mathematics suggests fundamental limitations. Just as information cannot escape a black hole's event horizon, information cannot pass between universes in this model. Each universe remains causally isolated from others, able to infer their existence through theory but never directly interact with them. This isolation creates what philosophers call an epistemological boundary, a limit to what we can know through direct observation. However, the mathematical consistency of the theory allows us to make inferences about what might exist beyond our cosmic horizon, similar to how we infer the existence of the interior of the Earth without directly observing it. The black hole universe theory continues to evolve as new astronomical observations and theoretical developments emerge. The Event Horizon Telescope's first image of a black hole in 2019 provided unprecedented confirmation of Einstein's predictions about these cosmic objects, strengthening the theoretical foundation of models that connect black holes to universe formation. As we continue exploring the frontiers of cosmology and black hole physics, the possibility that our universe exists within a black hole reminds us of the profound connections between the very large and the very small, between creation and destruction, and between the observable and the theoretical in modern physics. From that sunset over the Pacific that started my contemplation, to the mathematics of rotating black holes and expanding universes, the journey through this theory reveals the remarkable unity of physical law across cosmic scales. Whether our universe truly exists within a black hole remains to be definitively proven, but the mathematical and theoretical connections suggest a profound truth. The boundaries we perceive may be gateways to greater cosmic realities, and what appears as an ending in one context may be a beginning in another. As we gaze at the night sky, filled with stars and galaxies slowly receding from us in the cosmic expansion, we might be witnessing not just the vastness of our universe but also the interior of a black hole. A cosmic matryoshka doll of universes nested within universes, each born from the collapse of matter in its parent. This perspective transforms not just our understanding of cosmology but our very conception of what it means to exist within this vast and still mysterious cosmos.